Okay. Let me get my screen shared. Okay. So last that we left off on Monday, we were talking about how the operating system handles allocating space on a disk. And so we talked about contiguous allocation. It's sort of the same as a lot of these dynamic allocation problems that we've looked at, where there are multiple options for how we can sort of handle allocating this space to the files that need it. So we looked at contiguous allocation, where we just sort of allocate blocks in a row on the disk, but that had problems with external fragmentation, such that we have these open areas that don't necessarily meet the size of the next file that we want to allocate size for. And we have more of an issue here than we did with dynamic memory, because secondary storage is much larger, which makes compaction more time-consuming and difficult. And it's non-volatile, so the fragmentation is persistent. And it also has the issue of we don't know how much space we need to allocate per file. So count may need to only take up 2 blocks. It may need to take up 8 blocks. And if it ends up needing to take 8 blocks eventually, we haven't saved enough space for it. So the next thing we looked at was linked allocation. So linked allocation just allocates a single block at a time. And eventually we link these blocks together with a pointer at the end of each block that tells us where the next block is in the file. So this doesn't have external fragmentation because we're only ever allocating a single block at a time. And we can increase file sizes as needed by linking more blocks in. So all we need is a single available block. And we were just talking about the downsides when we left off in last class to linked allocation. So the first downside that we already talked about a little bit is the fact that direct access isn't cheap. So to find the position in the file, we have to start with the first block, follow that block to the next block, follow that block to the next block, and eventually get to the part that we can read or write something from. So if we want to write to random positions in this file, if we want to be able to sort of seek to a random position, write to it, seek to another random position, write to that, or read, same difference, it's hard to find the actual blocks that we need to access that data from. So it's hard to find where we are in a file if we're trying to access things directly. If we're just accessing things sequentially, linked allocation is great, because when we get to the end of a block, we just move to the next block and we're good to go. So this is only a problem if we're doing direct access. The second disadvantage is that we need a lot of space for pointers. Space required for pointers isn't free. Or maybe just space required for pointers is the disadvantage. So every block here has to have a pointer to another block. So we require, basically 4 bytes for every block has to be allocated to that pointer. It's not a lot of overhead, but it is, overhead that we don't have in contiguous allocation. Or 4 to 8 bytes per block. Depends on if we're in a 32-bit or a 64-bit system. So a 32-bit system would have 32-bit addresses, which is 4 bytes. A 64-bit system would have 64-bit addresses, which is 8 bytes. So depending on how big pointers are, we need that space per block for each pointer. So again, this isn't huge, but it is a small downside compared to contiguous allocation, where in contiguous allocation, we weren't wasting any space for pointers, or if we were doing sort of the contiguous allocation with linking those bigger blocks, we would have less pointer overhead because we only have to have a single pointer for each set of blocks rather than each individual block. And then the final disadvantage here of linked allocation is reliability. So the question is, like, if we lose a sector, we lose some part of this disk, can we end up losing the whole file even though we've only lost part of the disk? So if this file starts at 9, if we end up losing the block that holds 16, this gets overwritten in some way, the sector of the disk goes bad, something like that happens, if this part of the disk goes bad, where we have this block to 16, all we can access of that file is the part that's contained in 9, right? Because we've lost the data in 16. Now we've also lost the pointer to the next block. So because we're sort of storing the structure along with the data, we're not only losing some of the data, we're also losing the rest of the data because now we don't know where to find that data on the disk. And so it's going to be a lot more complicated to recover. Now, of course, if we lose 16 and the entire file is right there, we might just lose the entire file anyways. But the issue is sort of that we lose the structure of the file entirely, and that can cause us to lose a lot more data due to the fact that we lose pointers. We lose pointers if a sector of the disk goes bad, where before we'd just be losing data. So one of the optimizations on this that the book talks about that I wanted to mention is using a file allocation table. So right now, all of the structure of this file is stored with the files themselves. In a file allocation table, we have this pointer structure, but it's stored in a separate sort of entry. So we have the same links between blocks that shows us where we go to be able to access the entire file, but this is all stored in a separate table. So rather than having this in like an exact thing or in the files themselves, we have sort of a separate structure that holds all of these file pointer links, and then the actual blocks are the numbers that we have in this table. So this is sort of collecting all the pointers together in one place, so that one, unless we lose this table, we don't lose the structure of the files. And two, now we can maybe more easily load this table into RAM, for example. So like whenever it's all scattered throughout all of these different files, each time we look at a file, we have to load that into memory, read all of that data, find the pointer, follow that pointer, or we have to read that directly from disk, which is going to be a long, expensive operation. Here, we can load parts of the file allocation table into memory, read them, do all of the sort of jumping around, finding the block that we need to do in RAM, or further following through the caching system. And that'll be a lot faster than if we have to sort of follow those pointers on disk. So it's essentially the difference between following pointers on disk versus following pointers in RAM. And this file allocation table allows us to do that in RAM. So this can solve some of these problems. Basically, it collects these pointers into the same space. It makes direct access a little bit cheaper because we can follow the file allocation table instead of following these pointers on disk. And it helps a little bit with reliability because we don't lose pointers unless we lose this file allocation table. So you may recognize this from like if you go to your local drive here and hit format. It's not going to let me format that volume. Let me plug in a USB key real fast so I can show you the menu. Yep. So if you look at the prompt that you get whenever you go to format a disk, you can see that the most common option is either FAT or FAT32 or exFAT. So all of these systems on Windows are going to be file allocation table related file systems. So just something to be aware of, that this is a common format on Windows systems. Most of them nowadays will use NTFS, which is the new file system for Windows, but they do still have this sort of legacy file allocation table format. And usually if you're like interacting between Windows and Unix or Windows and Linux, using a FAT formatted disk is the better way to go, because Linux is capable of understanding a file allocation table format, whereas a lot of them don't have NTFS support built in. So just something to be aware of, not super important. So the next allocation type solution that we can use is indexed allocation. So this is sort of extending the FAT solution and providing direct access to files with an index. So basically trying to speed up direct access to files rather than using this sort of FAT file allocation table format. So with indexed allocation, we have an index block, and then we have the data blocks. So the index block just stores a bunch of pointers to all of the data, and the data blocks store all the actual data. So we basically just steal an entire block on the hard drive or on this solid state drive to store an index of where the rest of the data for that file actually is. So again, for the same file that we were looking at before, if we have this file Jeep that takes up some number of blocks, now instead of having links between all those blocks and just recording the start address, we just record all of the blocks in this index file, or in this index block. So we say their index block for Jeep is 19, and it has pointers to 9, to 16, to 1, to 10, and to 25, which are the same things that it had in this setup here. Just now these are all stored in a single index file rather than in the pointers in each of the blocks that we are accessing.
Sir?
Mm-hmm.
How do we know what order those blocks go in?
So it's ordered from the top of the file.
Oh, okay, just 9, 16, 1, 20.
Yep.
Gotcha. Okay.
Yeah, so it's just in sorted order of the blocks that are comprising the file.
Okay.
Yeah. Yep. So this is just, we reconstruct it by saying that, 9 is the first block, 16 is the second block, so on, that 25 is the last block. Just the same, it should be the same format as this diagram has here, where it starts at 9, goes to 16, to 1, to 10, to 25, and 25 is the last block there. So the main issue with this setup, this is really nice because again, we don't have external fragmentation because we can allocate in single blocks. We have faster direct access because if I know how big each of these blocks is, if I want to access byte number 20,000 in here, I can very quickly say, okay, 9 is 4,096, 16 is 8,092, so on and so forth. I can basically just keep adding and know that 25 is going to contain bytes 16,384 to 20 something. So I can very quickly sort of calculate, where the blocks are here, by just saying that, 9 is 4,096 bytes. Then 16 would be the next 4,096 to 8,192. 1 would be 8,192 to 1,228 or 288. The next one is 228 to 16,384, and then finally 16,384 to 2,480 is the last block. So I can just sort of math my way through where a piece of the file is. So doing that read of Jeep at 20,000 is much easier now because I know how many index, or I know the index of the file, so I can very quickly scan to the block that actually has that address. And so this allows us to do that. It allows us to do, index file formats and index sequential file formats as well, pretty cheaply. So the main issue with this is the space that we need for index blocks. So for small files, like let's say we have a 4K file, we now have an 8K file. So if we're only using a single block on disk, now we have to use 2 blocks for that single block. So we're basically doubling the overhead of small files. For very large files, as long as they are under the size of the index block, it's okay. But if we have a file that is bigger than what we can point to with, a single block of pointers, so let's say we get to the point that we filled up all of these entries and some of them are not -1. What do? Well, now we're out of blocks in our index block. So we need to find some way to make big files as well. So right now, this only really works well for things that are close to the maximum file size because we have very low index overhead at that point, low pointer overhead. And we can sort of fit the entire file in the index. But for small files, the index overhead is really large. For really big files, we can't fit the file index in a single block. So to handle these sort of larger index cases, we have a couple options. The first one is that we can use a linked index, which is just that each index block or the last pointer in each index block points to the next index block. So this doesn't really solve the sort of small file issue, but this solves the big file issue. This allows us to basically keep extending our index as much as we need, eventually getting to the point that we have enough index for the entire file. So solves large file problem by extending the index as much as needed, but doesn't fix small file overheads. So the other thing we can do, and this is again sort of a solution for large files, but not so much for small files, is to have a multi-level index. So this is very similar to what we looked at with two-level page tables. So two-level page tables solve the problem of needing to access a ton of memory or sort of store information about a ton of memory in a data structure. So we have sort of the top level that has pointers to the second level, and then the second level has pointers to the actual data that we're looking for. So this is the same idea here, where we have a top level index block that points to other index blocks, and then those other index blocks point to the actual blocks for the file. So two or more levels of index blocks to allow larger files. And again, this solves the large file problem, but doesn't really solve the small file problem. In fact, the multi-level approach makes the small file problem even worse, because now we have an index block that links to another index block that links to the file. So now we would have, 3 blocks for a single block file, which is sort of even worse here. But this does solve the large file problem. And then for this last one, I do want to copy over this image from the textbook, which is pretty nice. So the final solution is to use a combined scheme that has some direct blocks, so some direct index blocks, some indirect blocks, and then some sort of even more indirect blocks. So it sort of extends the multi-level approach to allow us to sort of limit these as much as possible, so we don't have the issues that come out of multi-level. So this has some, basically for large files, we have triple indirection. For small files, we still have that sort of direct index block approach. So we have basically multi-level depending on the, or multiple levels depending on the size of the file. So for small files, we basically have, a number of pointers to up to 12 blocks. And then the rest of that block would be metadata telling us, if we have a table instead, that's what we have instead of data. So we can either have pointers to the actual blocks that we're using, or we can have pointers to the tables that then point to the blocks. So this sort of shows if we have a small file, we have direct blocks just to data. If we have a slightly larger file, we might have a pointer or a couple pointers to tables, which then point to data. If we have a larger file, then we have a pointer to a secondary table, which then points to more tables, which then point to the data. And we could have triple indirection, where we point to tables to tables to tables to data. So this is just allowing us to be flexible so that we don't sort of waste a bunch of overhead in an inflexible system that requires like single indirection or double indirection for every single file. So this still doesn't quite solve the small file problem. We still have a good bit of pointer overhead because we have to take up a block for the index and then take up blocks for data. But this sort of makes it as best as possible without sort of running out of files or having excessive pointer overhead, because we have to sort of link together these blocks. Okay. So any questions on these allocation schemes? Okay. So then let's move on. So we talked about then how we allocate memory into this space. The last thing we need to talk about with disks is basically how do we handle the free space. So this is how we decide to allocate something into the free space that we have. What we need to know is how do we track how much free space we have and where that free space is. So because secondary storage is so large, we do need to think about how to handle the fact that we do have some significant space that might be available for us to use. So there are a couple different things that we can use here. The first of those is a bitmap or a bit vector. So we sort of briefly mentioned those in the intro to the course. Essentially what this would do is would say, you know, let's take an example here. Maybe let me grab one of these images. So if we have this example here, we would have a bitmap that just basically indicates a 0 if the block is allocated and a 1 if the block is free. So going through this structure here, we would have a 0 because block 0 is allocated, a 0 because block 1 is allocated, a 1 because block 2 is not allocated, 1 because block 3 is not allocated, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. And that's the whole thing. So we're just basically putting in a 1 if the block is white, meaning that it's unallocated. We're putting in a 0 if the block is gray, meaning that it is allocated. So what we can do then is try to quickly find where we have free space in this structure. So we have this bitmap. The common optimization on this is basically each bit is going to represent some block. We could go through and we could individually check each of these bits to see if they are zeros, to see if it's allocated, or to see if it's a 1, meaning we have free space. What the system is actually going to do is it's going to group these at least into bytes, if not into larger structures. So we can basically take this first byte here and say, is that equal to all zeros? If it is, then we know that that entire thing is allocated. If equal to 0, entire set of blocks is allocated. If not, some block is free. And so we can do this for a byte. We can do this for 2 bytes. We can do this for 4 bytes. Whatever the word size, word meaning like what the address size of the system is. Usually we have operations to check equality on an entire word. So realistically, the OS would be able to check, is any block free in this entire 32 bits? And if it does find that some block is free because it's non-zero, that means that we can find the first bit that is free, or the set of bits that are free, so that we can allocate into that region. So that's all we have to do here is basically check to see if the entire thing is 0. If the entire thing is not 0, then find the first bit within that that is non-zero. And at that point, we're looking through a small enough set of, or a small enough amount of data that it's pretty easy to find where the first bit that's non-zero is. Okay. So this does require some extensive storage, and this one's in the book, so I'm not going to break you out into rooms for this, just because it is pretty quick. So if we have a terabyte disk with 4 kilobyte blocks, we have to maintain a set of bits that is large enough to represent that entire terabyte, because that when we first start up the computer, when we first start installing things, that entire terabyte will be free. Or some significant portion of that terabyte will be free if we have the operating system installed on it. But if we put a new disk in, that entire terabyte is free. So we need to maintain a bitmap for that entire bit of space. And that means we have 2 to the 40th is 1 terabyte. 2 to the 12th is 4 KB. So we need to have a bit for every terabyte divided by 4 KB. because we have that many blocks. So 2 to the 40th divided by 2 to the 12th equals number of blocks equals 2 to the 28th. All right, so we can just subtract since we're dividing a power of 2 by another power of 2. So we have that many bits, or sorry, number of blocks equals number of bits in the bitmap. So we have 2 to the 28th bits, which means that we're going to divide that by 2 to the 3rd for byte. 2 bits is going to be 2 to the 25th bytes. And this is in the book, so again, you're welcome to sort of retrack this, try for another problem, which means we're going to have 2 to the 5th megabytes. So 2 to the 20th is megabytes, 2 to the 5th is going to be 32. So we're going to have 32 megabytes of space that we have to use just to store the bitmap. So this is a pretty large amount of space that we're taking up to store this bitmap to be able to sort of efficiently map this. So this 2 to the, this 32 megabytes can either be sort of disk overhead. It might be stuff that we have to store in RAM at some points, which means that we're taking up a significant portion of our RAM to store this bitmap whenever we need to allocate file space. So this is a significant amount of memory that we're using for this. That said, in the context of like, a terabyte, 32 megabytes is not that huge, right? This is taking up some of our space, but it's not like it's taking up a full gigabyte or something like that, right? And so this is part of the reason that, like, if you look at your hard drive, when you install a hard drive into the system, you expect to see that the disk size is 1 terabyte. It's never actually 1 terabyte. It's not that the vendor is, getting one up on you. It's just that there is some overhead for these structures to make sure we know how many blocks are free, all this extra metadata that has to be stored on the disk depending on the file system. So, the actual physical space on the disk might actually be a terabyte, but what you're actually going to see in your operating system that it's going to give to you is not actually going to be a full terabyte. Maybe it would be nice if the disk manufacturers would give you a terabyte plus some overhead, but that's not the way the world works, unfortunately. So other structures that we can use to maintain this, just like we maintain a linked list of the allocated blocks, we can also maintain a linked list of the free blocks. So the free blocks of memory can just basically be a list that is linked together. So, where we have this structure that has sort of, 0, 2, 3, we could have basically a linked list that says, file free, and free would be a linked list of 0, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15. Every white block in this diagram would be in a separate list and sort of linked to each other. So this depends on the file system. We could also have sort of an index that shows us where all the free blocks are. But essentially the idea is that we can have a linked list of all of the free blocks. And so when we need a new block, we just say, take one off of the front of the list and give it to whatever file needs it. So that system, it works. This does require the data structures, the extra pointer overhead to maintain this list of free blocks, but it can be, somewhat efficient to sort of just keep track of all of the numbers of blocks that are free currently. Another extension that we can do is to use grouping, which is essentially the free list or the index version of this, where we place n-1 free blocks into a block, which can store a total of n pointers. So we have a block of device memory. We list a bunch of free pointers in there, and then the last address in there links us to the next block that has free pointers. So this is just the index method of the linked list style here, that we instead of sort of having all of these links broken up in memory, we just sort of group them into disk blocks with each other. Another approach is counting. So counting takes advantage of the common characteristics that several blocks will generally be allocated and freed at the same time. So this is sort of going back to contiguous allocation. If we look at contiguous allocation, right, we generally have like a file that starts at 0 and goes for 2 blocks, or a bigger file that starts at 19 and goes for 6 blocks. And so counting can basically take advantage of that same property, that these files are going to use some number of blocks in a row, and that we can sort of track on the free space in a sort of condensed format where we say, okay, block 0 is free, and every, the 5 blocks after block 0 are also free. And this way we can just maintain a list of the free blocks and the number of blocks after that block that are free. And the OS can sort of more quickly search for a region to allocate based on the number of free blocks within that region. So we could have a tree that says, basically like a tree that is ordered by the number of free blocks, for example. So we have a balanced binary search tree where we sort of have like, maybe insert something here for that. So we could have a tree that basically says like block 0, size 5, and a little bigger. We could have a tree that is structured so that this is size 2, block 16, block 28, size 7, something like that. So we basically have this tree that is a binary search tree. So we know that if I need to find more blocks, I search to the right side. If I need to find less blocks, I search to the left side, so on and so forth. And if we keep this roughly balanced, then we can have a sort of quick search through this tree to find the space that we need. If we don't keep it well balanced, then we might have more trouble. So we can sort of see the structure here, that we would have some sort of a tree that can keep all of the available nodes in the system in that tree, and sort of just have a count of how many blocks are free at that location, so we can quickly find the size of allocation that we need. So this is sort of critical for a contiguous allocation system, nice for other systems if we need to find a large number of blocks at the same. Okay. And then the other approach to this is again sort of counting, but this is for very large file systems where it's too difficult to sort of keep all of the free spaces in memory. So you can keep what is called a space map that contains a log of allocations and deletions, including counting information. So this is essentially the same structure as we have above, but it's kept in a log file instead. So it might just say like deleted block 0, size 5. Deleted block 18, size 9. Allocated block 4, size 2, something like that. So this sort of a log might be kept to basically allow you to reconstruct this tree when you need to perform allocations. So otherwise, this is just kept as a sort of small file that only has the information that you need in it. And when you do need to perform an allocation, you load this file into memory, perform any sort of compaction that you can perform on it. So if you have multiple blocks in a row now that you can make into a bigger size, you can do that at the time that you load this, do the allocation that you need, and then basically rewrite that log back to disk. And then this allows you to basically just maintain this running log of the system rather than keeping all the information in memory at all times. So this can be more efficient depending on the system, but it's very sort of a specialized thing here. That I think they mentioned this in sort of context of a specific system, the ZFS file system that's made for very large disk structures. And so if you're trying to very highly optimize your disk usage, if you're Amazon or someone like that, that's sort of like Dropbox would be a good example, that's like providing cloud storage, wants to really make sure that they're saving as much as they can on hard drive space, because that's going to save them money over time and cause them to be more valuable. Then you might want to care a little bit more about this type of a system where you can very quickly allocate free space. Or maybe it might be slower to allocate new space, but it is easier to maintain the list of free space on the drives. Okay. Any questions on free space management? Okay, and we're almost done. So then the last thing to talk about is the one extra special thing with SSDs. This is a sort of a footnote in the book as well, but we should talk about it so you're familiar with the term, which is that SSDs require extra care when you're allocating and deleting blocks of memory. Because they can't be overwritten, you have to erase it and then write the disk. And we have this sort of limit on the number of writes you can perform on an SSD. And these take a long time to perform on the disk. So basically, we have to have a method to inform the storage device that a page is free, that some block of memory is free and can be erased so that it is ready to be overwritten in the future. And this mechanism is known as trim or unallocate. So basically, just the OS has to be aware of this to be able to tell the SSD that it needs to get rid of its space and be ready for reallocation at some point in the future. Okay, so really just terminology for you for your future studies / working. Oops, I did not want to hit that. I want to log in. So we have a Kahoot to finish up today. I'm going to save you some time on either Monday or Friday for softs, because I don't think 13 minutes is going to be quite enough. I know there's some extra questions for you this year because of the fact that we did online learning. So there's a bit of extra stuff for you to answer. So I want to give you a little more time. So we'll save that for Friday. Again, I do want to mention Friday, we're going to have a special topic. So I think 3 of you still need to vote if you want to have an impact on here. Right now, we have a tie between security and error correction and detection. So if you want to have an impact on what we learn on Friday, please vote before the end of the day today so I can have time to make notes up. But yeah, Friday we will do softs. I'll give you some time for that. And then we will do, or we'll probably do first a brief topic from this list, likely security or ECC. And then whenever we're done with that, we will move on to softs. So just please remember to vote if you want to have an opinion on that. And we'll finish up with the Kahoot. Sorry, was that?
Is Tuesday the last day of classes?
It is, yeah. So next Monday is our last day. So Monday is going to be a review for the exam. And again, another reminder that if you are unable to make the exam time, which is going to be, let's double check this again. So our exam time is next Thursday at 9:30 a.m. EST. If you are unable to make that for some reason, please let me know as soon as possible so I can work out what we need to do. But unfortunately, due to guidelines from higher up, I have to basically give you the exam from 9:30 to 12:30 and then be done. So I will, I'll pass it out. It'll be electronic, same format as before, but it'll be that 3-hour window for you to do the exam. And then you'll have to turn it in on Blackboard at the end of that period. So obviously I'll cut you some slack if you have issues with scanning or taking pictures or anything, but it does need to be done in that sort of 3-hour window so that you can move on to your next exam if you have one, which at least one of you is going to have an exam. I guess just one. I don't know about the rest of you, but I know unfortunately, Rupam, you're going to be going from this straight into compilers.
Wait, so it's like compilers is at 12:30?
No, it's at 1:30. But
I guess there was a lunch break.
Yeah, there is a lunch break. Yes, but yeah, so you may have an exam right after this, unfortunately. So yeah.
Appreciate the love, Ethan.
Yeah, he can. I'm sure he can handle it. He'll be fine. But yeah. Okay, so let's get started. First up, which storage technology can only be written a limited number of times? Okay, so we just talked about it. So SSDs have a limited number of writes that you can perform. And they have to be erased first, which means they have this what's called a wear out factor you can only write to them a limited number of times. HDDs, it may eventually wear out, but it's sort of like a much longer time that they can go, and it's not much of a factor. Like the mechanical parts will fail before the disk can't be written anymore. T-Jizzle was the fastest on the buzzer there. Okay, next up. Which storage technology is generally less expensive per byte? Nice, yeah, so HDDs. So usually hard disks are quite a bit less expensive because they're larger, bulkier, and have some issues with, startup time and things like that. Okay, Stewie taking the lead. Next up, which layer of the file system implementation interacts directly with storage devices? This is a harder one. Okay, yeah, so this is from the chart in the notes. Right here. So this is the I/O control level, which interacts directly with device drivers. So that's what we're looking at there. Got some people there. Next up, which layer of the file system implementation tracks unallocated blocks? Okay, nice. Yeah. So this is the file organization module. It's sort of one level below logical file system. The basic file system interacts directly with the sort of, or like issues generic commands to the device drivers. So I/O control interacts directly with devices. Basic file system interacts with that. The file organization module is sort of like aware of the generic structure of a disk, but not sort of directly issuing commands to it. Okay, on a hot streak there. Next up, which layer of the file system implementation does the user interact with? Yeah, so the logical file system is what we're looking for here. So they sort of modify the files and directories. I maybe should give you credit for the lower levels because technically the user does kind of interact with like device driver installs and things like that. So if you answered that for that reason, I'm sorry, that maybe should have been an answer, but generally the user just interacts with the logical file system for the most part.
Thanks for jinxing me, sir.
Sorry. Okay. Which allocation method does not suffer from external fragmentation? Okay, yeah, so the last two are both good. Contiguous allocation is the only one that does suffer from external fragmentation because it doesn't have, it doesn't allocate in single blocks. So it sort of allocates more than one at a time, and that means if there aren't enough contiguous blocks available, it's going to fail to allocate, and it will fragment over time. And T-Jizzle's on a hot streak today. I don't know if anyone's going to catch him. Which allocation method has the least pointer overhead? Okay, yeah, nice. So that's a bit of a tricky question. The least is the critical thing here. So contiguous allocation doesn't have pointers. The sort of extension to it is that you can have a pointer at the end to point to another contiguous allocation, but even that is going to have less than linked or index, where we have pointers for every single block. So contiguous allocation is definitely the correct answer there. So we have a, so Ukraine is better in third. Gollum in second. Nice work. And then perfect score. Nice work, Tyler.
First time ever. Woo!
Yeah, way at the top there. Perfect score. Nice. And we've got runners up, but it's blocking them out. Sorry. So nice work, Rupam and Stewie in the end there. So good job. That was pretty solid. There will be a very short homework on this due Tuesday of next week, just to give you a couple practice questions, trying to prepare you for the exam, like what you might see on this type of stuff, so on chapters 13 and 14. But I'm going to make it very, very brief because of the fact that it's such a short fuse. Otherwise, just keep in mind, vote on Piazza. Oh, we just have one left, but it's not showing me the results. So vote on Piazza if you're the one person that hasn't voted yet. Otherwise, we'll have that topic, whatever is the winner, for Friday, and we'll do softs on Friday as well, and then review on Monday. So otherwise, unless there are any other questions, I will see you on Friday.
Thank you, sir.
Thank you, sir.
Sorry, Kira, can go ahead.
Thank you.
Oh, Professor, I had had that timing code run the whole class, so let me see if there's anything interesting.
Okay, cool.
Professor, I had a question.
Okay.
So I was doing the homework that was supposed to be due now.
Okay.
But I was struggling with the parts that talked about the pages.
Okay. So which ones in particular?
Just like all three of them.
Okay.
I just don't know how to do it.
Let me look at it real quick and sort of page in, pardon the pun, what questions we're asking about. So is this the ones at the end then? So
there's like question 1, question 6, and question 8.
Okay. Okay. So question 1 is sort of looking at, you have, these 1 kilobyte pages in a 16-bit address space. So you have 16 bits to use, right?
Yes.
So then how many of those bits get used to represent the offset for 1 kilobyte pages?
I need to pull up the...
So essentially the question I'm asking is like, what power of 2 equals 1024?
It's 10?
Yeah.
12.
So 1 kilobyte is 1024 bytes, meaning that we have 10 bits to represent each byte of that 1024 bytes.
Yes. Would that be a page offset?
Yeah, so that's the page offset. And then the page number is just 16 because we have 16 total bits minus the number of bits that we're using for the page offset.
So that'd be 6?
Yep.
Wait, that's the frame number?
That's the page number.
Oh, okay. The page number is 6?
Yeah, and then the frame number is coming from a different thing. So that's being derived from the fact that we do have 16 frames.
Okay.
And there are 64 pages. So 64 pages should be the same as 2 to the 6th. So like 2 to the 6th to 64, that means we have 64 pages. So 16 frames means we have 2 to the blank frame number bits.
2 to the 4?
Yeah.
And that's the bit frame number?
Yeah, that's the frame number.
Oh, wow.
Yep. So in this system, we have less frames than we have pages because, we have this mapping from pages to frames, but it doesn't have to be 1-to-1.
Yeah.
We can have less physical memory than we have pages. Okay.
Yep. Yeah, that makes sense now.
Okay. And I think 6 should be sort of a similar problem. 8 should be 8's a little different. Do either of you have to go somewhere?
I don't.
Beck, do you have class after
I don't
this?
either.
Okay. Do you mind if I sort of finish with him and then finish with
Sure.
Austin, and then we can chat? Okay. So for 6, this is a very similar thing. So we have 64 bits total. We have 4 kilobyte pages, so you compute the page offset from that. And then essentially after that, we're just remembering that the TLB bits for the index are the last couple bits of the page number. So you basically want to divide up that like OX 01, 2, 3, 4, 5, 6, you know, A, B, C, D, E, F into the page number and page offset bits. So for 4 kilobytes, that's 12 bits, right?
Yes.
So the last 12 bits, each hex digit is 4 bits. So DEF is the page offset. So 01, 2, 3, 4, 5, 6, 7, 8, 9, ABC is the page number. So the last few bits are going to be the TLB index. And what we want to know is like, what are the index bits coming out of that? So for 256 entry TLB, how many index bits do we have?
That would be, let's see. Would that be 8?
Yep. So if we have 8 bits used for the TLB and they're the last bits of the page number, what's the hex number that we're using?
Would it be the 8 coming out of, let's see, C, B, A, and 9?
So it'd be just the 8 at the end, which 8 bits is 2 hex digits, so it should just be BC.
Oh, okay.
Yeah, because those are those are sort of the last 2. They're the last 8 bits of the page number.
Oh. So it'd be, so BC.
Yep.
Would BC be 127? Oh wait, is that?
I think it has you give the answer in like OXBC.
Oh, OXBC. Okay.
Mhm.
I thought it meant like more.
No, yeah, it's just asking to find the bits that would be used. So, mostly just looking for understanding of like how the TLB works and how the address gets divided there.
All right, that makes sense too then.
Okay. And then 8. So 8 is looking at again 16 bits in the address, 1 kilobyte page size. So we already computed that, right? That we have a 1 kilobyte, page is 10 bits of that 16-bit address space. And then it's asking first, in a conventional single level page table, how many entries would we have? Second, if we have an inverted page table, how many entries would we have? So the trick here is basically just remembering what those 2 layouts look like. So for a conventional page table, we have 1 entry per page of memory. So basically, we just need to know how many total pages are there in this system based on how big the page number is.
Well, the 1 kilobit is the 10-bit page.
Yep, is the 10-bit page offset. So
yeah.
So then, how many bits is the page number?
So let's see. So we said it was 10 bits for the page offset.
Mm-hmm.
Let's see.
And 16 bits total, so we have 6 left, right?
6.
So then 2 to the 6th is the number of pages. Basically, because we have 6 bits, and each bit can have 2 different values, we have 2 to the 6th possible values that we can have for a page number, which means that's the number of pages we have. So it should be 2 to the 6th is 64. That's the number of pages in a conventional single level table.
Wait, is this for pages or entries, or is it the same thing?
It's the same thing because we have to have an entry for each page.
Okay.
So that's like how this works, right? Is we split the address up, we find the page number, we use that to map into the table. So we say that, you know, I found page 50. I'm going to look at page 50's entry, and then I'm going to find the frame number for that page.
Okay.
And so then the inverted page table, do you remember what the structure of the inverted page table sort of looks like?
I'll need to pull it up again on the notes.
Okay. That's okay. So it's a, I mean, it's essentially, it's just flips it. So in a page table, the conventional one, we have page to frame, and we have an entry for each page. In the inverted page table, we have frame to page instead.
Frame.
Yeah. So we have an entry for each frame in an inverted page table rather than an entry for each page in a conventional page table. So essentially the second question there is just how many frames are there total given a 1 KB page size?
10?
No, so we have 32 kilobytes of physical memory total. Did I miss you saying something there?
No, I'm still looking at it.
Okay, gotcha.
Is it 15?
No. So it's just it's one of these that
Is it 32? Is it like 32,000?
No, it's just 32. So we have 32,000. I mean, we have 32 kilobytes of physical memory.
Yeah.
We're splitting that into 1 kilobyte chunks. So it's just 32 entries total.
Oh, is it just like, so so 1 kilobit page size, we just need 32 of them.
Yeah, to fill up that 32 kilobytes.
Oh, okay.
Yep.
Okay, now that makes sense now.
Okay. Cool.
All right, that's it.
Okay, awesome.
All right, thank you.
Yep, see ya. Okay, Mr. Beck.
Okay, so kind of interesting. I got it faulted right as I pretty much was saying, oh hey, I've been running the thing the whole class.
Okay. What size did it fault on?
8192.
Okay, yeah, I think the buffer that's there is too small. Yeah. So yeah, I was looking at that as we were talking at the end of the meeting, and then realized that yeah, the like buffer size that they define is I think it's 4096 bytes.
Yeah.
So we need to increase that if we want to go the whole way up. And then we can see if it still fails. It might not be allowed to use that much memory.
Yeah.
But yeah.
But it does look like it is doubling each time. There isn't, and it gets a little faster. It's not a full double, but it's like a little less than a double for each doubling of byte space.
Do you mind leaving that up real quick? I'm just gonna real quick add to my chart here. Yeah, it does. Yeah, it definitely doesn't double.
And I was thinking, so like we talked about how it's like right lines are like gridded, and I would think that if that grid, it's not doing it like it does. It's not like reading and writing like it does in DRAM, where it drops a row down and then selects what it needs from that row, and so you would see like a big slowdown with reads and writes and
right
like row size. So I'm wondering if maybe there's another way we could try to pin down what the row size is.
Yeah. That's definitely tricky to tell. I don't know if there's any information in their stuff, like in the The other place we can sort of look is to see if there's any information in those white papers that might tell us how many there are. Because otherwise I'm just kind of, we can spitball and try to think about factors that might lead us to the right, the right goal here. And we can definitely just try different sizes and see, does that make an effect in the actual row hammer attack? But then we're just, sort of blindly stabbing and hoping we hit something.
Yeah.
I mean, I think maybe what to do for now is to just assume some sort of reasonable size. So it looks like, and I can share this with you and everyone else.
Do you have all the values down?
Yeah, I have all the values down. But let me, I'm just going to hit a couple other people on this real quick. So they can all see the data. So I sent you a Google Doc, but I can present it too real quick here. So this is just the data that you got there, overheads compared to the previous byte size, so we can see if it's doubling or going over double. Obviously, it's not over doubling. And then looking at time per byte. So like where we're sort of getting the most efficiency out of this per bits or per bytes being written. It's obvious like it does seem to be sort of gaining some performance from grouping things together. We could definitely try some of these sizes. So I would say like maybe trying like a 128 or 256 byte writes, or like Dr. Eck was talking about, maybe like 8 or 16. Some of those ranges would be good to sort of focus on for initial tests. So just like make sure that you write like FFFF into each of those bytes, because we do want all ones to be written, not just like the last one in the bit pattern. We could try like a couple different things and basically just like, take in that 256 array that they have, pick out, either write the whole first half of it for 128 or double it and look at, 256, or, pick out every other row and write 8 bytes at a time, or every 8 bytes right to that. And basically just try some of these sizes and see if you write all ones, if you write all zeros, if you write like a staggered pattern of zeros and ones, like do the A or 5 value for each byte. We can see if any of that works. So I think that's like initial reasonable test to try to run. So, looking at each of these byte sizes, just writing some of those bit patterns and see if anything pops up. And if you want to like, continue to share code with me over the next couple of days, like my research days tomorrow. So if you work on this at all, you're welcome to like share code with me on Embed or, via Google Drive or whatever is convenient for you. And I can sort of, help out with writing that test case. I'm going to try to restart my computer after this and see if I can get the board that I have working, and I can play around with it a little bit as well and help you out with the actual code for this.
Okay. Yeah, I'll see what I can get to. I present my capstone tomorrow, so that's what I'm finishing up. But I'll see if I can't get some stuff done before Friday.
Okay. What day or what time did you say that was tomorrow?
It is 15:10 tomorrow.
15:10. Okay.
I can send an invite. I was going to include Dr. Rackvick an invite. I can include you on that if you'd like.
Okay, cool. Yeah, I have fishes in my compilers class, so wouldn't mind coming to see what the two of you did. So cool. Okay. Well, yeah, let me know if you have any issues, you run into any problems. I'm happy to help out whenever. So nice work.
Okay. That was good. Thank you.
Yep. See you.
See ya.